So today we will continue our discussions on the cross-point memory. And last lecture we talked about emerging memories. And there are two kinds of array architectures. One is this 1T1R, and then the other one is this cross-point array, or sometimes we call crossbar array. So we already started the discussions here. So the idea is to get rid of the access transistor. Then we can achieve this 4F square in the 2D plane. So here the idea is that we have the word line and bit lengths perpendicular to each other. At each cross point, we have the memory device. So typically, it's like a resistor, like R1, phase change. And then to address the sneak path and the unselected cells issue, we introduce this selector device, and we will talk about more details later why we need this kind of device. So I would say the cross-point array is more compatible with like R1 or phase change memory, because in this case, we need certain on-off ratio to guarantee the sense margin. So the STT-MRAM we discussed earlier, which is similar to the R1 phase change memory, is a variable resistor, but the on-off ratio, let's say the on-state resistance and off-state resistance, the ratio is only about 2. So it's pretty small. And it will become very difficult to satisfy the sense margin if we have this cross-point array with the MRAM. So typically the cross-point array will be suitable for the R1 or phase change memory. So here you are going to integrate the selector and then the R1 device in series and vertically. So this will be sandwiched between the word and bit line. So you can have this 4F square compact high density array. So let's talk about the array level operation. To write the data into the cross-point array, there are different kinds of write scheme, and one of that is widely used. This is called the V/2 write scheme. So here we show the bipolar operation. For example, you have the R1 devices. You need the positive voltage to set the device from the high resistance to the low resistance state. And then you need the negative voltage to reset the device from the low resistance state to the high resistance state. So here for the set, what you are going to do is to select certain cells you want to write one, and then you are going to apply the right voltage. For example, here we write to the overline, to the rows, and then you ground the bit line, which is the colon. So you have the full VW across the memory cell. So you can write the device. But then you will have this half selected issue, right? So because here on the same row, you have other devices, like those devices, right? You do not want to write those devices. Then what do? You have to inhibit, right? Similar to the NAND flash, we talk about that. So in this case, how do you inhibit? So you can apply half-way write voltage to the unselected columns, right? So if you have half voltage here, then effectively you only have half VW across those half selected cell. So here the underlying assumption is that the half selected cell will not be programmed. Okay, it may be under some disturb, but it won't be programmed. So this is for the unselected cell along the same row, those cells. Then here you will also do something for the cells along the same column, right? Because here, then you will also apply halfway right here. Okay. So then for the unselected cell along the same column, you will also have half V across those cells. So those won't be programmed. And then for the totally unselected cell, which is outside this selected column or selected row, for example, those ones, you see that they will have 0 voltage across that, right? Half V and half V. Then they will have 0 voltage across that. So you only have the selected row and selected column, under the half select condition. So this is how you write the data, for example, here to the high to low resistance state. Let's say to write data 1. And then if you want to write data 0, you have to reverse the voltage polarity, right, for this bipolar operation. So what you can do is simply reverse. So that means the selected rows will be grounded, and then you apply V right to the selected column. So this cell will have a negative VW, right, across that. So compared to the positive VW here, so here I have negative VW. So that will reset this cell or write 0 to the cell. Then similarly, you can apply half V to the other unselected columns. So again, you can double check that those cells will have negative half V across that, and also similarly to those cells. And then again, for those totally unselected cell, they will see 0 voltage across. So that's the principle for this V/2 red scheme. And yeah, so here you have to do it in 2 steps, right? Because red 1 and red 0, because the voltage polarity is reversed. So for example, if you want to write the data, let's say 8-bit data, like this 00111010, then you have to do it in 2 steps. First, you select those with ones, do it in the first step. After that is done, then you select those with zeros, and then do the second step. So in the 2 steps to finish this 8-bit data. So any questions?
Was this an unconfused between source and drain, or is it defined differently for these steps?
Those cells are 2-terminal device, right? You only have 2 terminal, like a resistor. Yeah, voltage across that, just 2 terminal. There's no gate, right?
So this is like opposite to what we do in NAND flash. Like in NAND flash, we do a first erase operation and then we do program of the page. And here we
So okay, so that's a good question. So in the land, because of the organization of the land, we always do the erase entire block, and then we program page by page or row by row, right? So here actually you have different options. So what I described here, this 2-step, right? So you write ones and write zeros, because here you can do random kind of access. But also you can do what you just proposed, right? We can erase entire, let's say, let's say write zeros all the row, and then you pick individual cells, which you need to write 1. You can do that, right? So this one you have the flexibility to do the random access. So that's why we pick those 1 and 0 separately. But of course, you can do the entire row erase and then do the individual cells to be programmed. But then that will probably burn more power, right? Because you unnecessarily erase some of the cells, right? So okay. So then there's another red scheme that could be used. That is called V/3 scheme. Okay. So here, again, this is for bipolar operation. So let's say what you can do to write the data 1 here. You can apply V-write to the selected row. And again, you ground the selected column. So here again, you have the VW across the cell, which you can write the cell. But then here the trick is that for the other unselected cell, you see the different color here. So for the unselected row, you are going to apply VW over 3, okay, for all the unselected rows. And then for the unselected column, here the yellow lines, you apply 2/3 of the VW, okay? Then you can check what is the voltage across each cell, right? So select cell, of course, you will see the full V right. And then for this cell, you can check those cells. You have VW, and then here you have 2/3 of the VW. So effectively, you have VW over 3 on those cells, right? So this is smaller than V over 2, right? So potentially this could help with any disturb, right? You have smaller voltage across those unselected half-selected cell. So that could minimize the disturb. So here then for the same column, you can also check like those cells will also have V over 3, right? On those cells. Oh, good. Then what would be the trade-off? The trade-off here is that you check those cells, okay? Those cells will also have V over 3 across that, right? So here, because you have V over 3 around from the row and 2/3 VW from the column. So effectively here, you also have the V over 3, right? So the difference is that for all the cells here, you have V over 3, except this one, right? So then compared to the previous, this one, right? So here, those cells, right, will see larger disturbed voltage. But then for this totally unselected cell, they will say 0. So they are kind of different. But then here, all the other cells will see V over 3, right? So each will see less disturbed voltage, but all of them will say that, okay? Similarly, you can look at the reset operation. You just reverse the voltage. I will skip the discussion. But the same conclusion, only this cell will say negative V right voltage. Other cells will just say 1/3 of the voltage. Okay. So here then, you will have some homework or maybe exam questions to calculate the total power consumption between those two schemes. So you can imagine that this V over 3 scheme may burn more power for the entire array, right? Because here all the cells will have like V over 3 across the cell, so you will pass some current, right? You have voltage difference, then you will pass some current. So it seems like entire array is burning the power, right? And then the V over 2 scheme, only here you see the selected row and selected column, you have the voltage difference. And then the other cells ideally will see 0 voltage. So potentially this one could save some power, but then it has higher risk of being disturbed because here you do have like V over 2 voltage across that. So any questions here? Okay. So then we talk about the read scheme. So read will be easier, okay, than the write, because the write will have to deal with those inhibition. So the read, we can read the entire row in parallel. So what you can do, there are two kinds of sensing. We are going to discuss the sense amplifier design as well later in the array level design lecture. So basically you can do the current sensing versus the voltage sensing. So if you do the current sensing, what you can do is to apply the read voltage, which is smaller than the write voltage, right? If the write voltage is 3 volt, maybe read is less than 1 volt. And then you can turn on this entire row, and then you ground all other rows, and then all the columns. So the columns might be virtual ground. You can have some virtual ground there. So this will generate the current, right, to the bit line. And then this current will sync to the sense amplifier, which will have some current input stage, could be virtual ground. So depending on the current, then you can sense this resistance high or low. Then you can detect the 1 and 0, right? So you can do this in parallel, okay? Current will flow this way. Or you can do the voltage sensing, right? In the voltage sensing, what you can do is to pre-charge, if you recall, right, like a SRAM, DRAM, it's all voltage sensing. You pre-charge the bit line. So here you can pre-charge the bit line to VR. That means there are some preset cap, right, around the bit line. Then the read voltage, okay, will decay. So here you ground the selected line. So then you have the current through this resistor. Depending on the resistance, the current might be high, might be low. Then that can decay the bit line with different rates, right? Then the bit line voltage will decay over time, and then you can determine a time to sense. And then to minimize the currents from other unselected rows, you can bias those unselected rows to be the same read voltage. But still, there could be some, let's say, contribution from the other rows, because here this bit line will decay, right? So that means it will be lower than VR. So it could, generate some sneak path to the bit line in this voltage sensing mode. So we have to cut off those, okay? That's the role of this selector. We'll talk about that later. So this is the voltage sensing, okay? Any questions? And later we will talk about the actual circuits for the current sensing and voltage sensing in terms of the transistor schematic. Okay. So then let's talk about the selector and the interconnect resistance or parasitics in this cross-point array, which is important. So the problem with this cross-point array is that we have so-called sneak paths, okay, and also the interconnect resistance. So because you have those wires, right, VLAN, BitLAN, so the wires will have some wire resistance because the metal, is not perfect, right? You have some resistance. So that means from cell to cell, you have some parasitic resistance. Of course, you have parasitic capacitance as well, the BitLAN, VLAN capacitance. And then the sneak path is through the unselected cell. For example, this is a selected cell. So you want the current flow mostly through this selected cell. But the unselected cell, because it's a resistor network, right? The current will flow anywhere, right? So you have resistors, then current will flow anywhere. If it's a linear system, if you apply voltage here, the current will flow anywhere in the network. So this, for example, this yellow path is unwanted, right? So this is called the sneak path. We have to minimize the current from the sneak path. Okay. If it's pure resistor like RRAM phase change memory, then there's no way to block those sneak paths. So that's why we introduce this selector device to cut off or minimize the sneak path current. Okay. So here the interconnect resistance, this wire resistance, will introduce IR drop. What is IR drop? I is current, R is resistance. So I times R, after each segment here, your voltage, I times R is voltage, right? Essentially it's a voltage drop. So here you apply some voltage from the edge of the array, but this voltage will, drop after you pass each segment of the array because of the wire resistance. If the current is large, or if the resistance is large, then the voltage drop will be significant, right? Okay, so then let's talk about the selector device, which is essential to enable this corresponding array. Without the selector device, the corresponding array memory will not work. Okay. Capacitance will, always affect your speed, right? But it won't affect your sense margin or something, right? There's no voltage drop or current drop across your capacitance. Your capacitance will only slow down the signal propagation. Right? So here, what is a selector? Okay, ideally, this is what you want. So because here you have the resistive memory like R1, phase change, or whatever. So essentially, you have two resistors. IV, current versus voltage of the resistor is just a linear line, a straight line. And of course, you have high and low resistance states. So you have two slope, right? Let's say this is low resistance state, this is high resistance state. So here, the selector is going to introduce this nonlinearity, okay, in the IV. So you want some cutoff below some threshold, okay, ideally. If it's bipolar operation, you want the cutoff on both, let's say, positive and negative side. You have some threshold voltage, essentially. So below the threshold voltage, then the current is negligible. And above the threshold voltage, this selector device fully turned on. So it's like an ideal switch. You want an ideal switch, but this switch is not a transistor. You want a two-terminal switch. Previously, you have 1T1R. It actually provides the same functionality, the transistor, right? Turn on the gate voltage, then it's like a switch on and off. But it's a three-terminal device. So here, what we want is a two-terminal switch, right? Two-terminal switch. That's the difference between this selector and transistor. Transistor is a three-terminal switch, right? So if you combine the S and R in series, right, in each cross point, you have the selector. So basically, what you want for the selected cell, the switch, will be turned on. Then you will have the current pass through, and then go through the resistor. And then for all other unselected, or even include this half-selected cell, you want this switch to be open, so no current flow. So if you combine the R and S, this is how it look like in terms of the IV. So essentially, you are going to cut off the current below the threshold. Below the threshold is almost off, negligible current. And above the threshold, because this one is fully on, then you do have two curves depending on the state, the low and high resistance states, or let's say your 1 and 0. Okay. So you are going to read at here some this is like if this is your right voltage to switch from, let's say, low to high, high to low resistance states, or let's say set from 0 to 1, then you're going to read somewhere here, right? You can still detect two currents at lower VR, read voltage, but this VR is to be higher than this threshold for this selector VT. So this is ideal selector, but in reality, there's nothing like a straight line, like below that is all 0 and above that is like, fully turned on. In reality, there's no semiconductor device can provide this, okay? So then in reality, this is what you may have, okay? So what you can get, for example, this is in the log scale, okay? It's like the subthreshold region of the transistor. We always show the current in log scale, and then voltage, of course, in the linear scale. So here, if your selector has this exponential IV, exponential current versus voltage relationship, that means at small voltage, then the current will exponentially decay, right? So here, this is the slope for the exponential decay. So if you have this selector device provide you this kind of bidirectional exponential curve, then if you combine this selector with the R1, this is a real R1 device, kind of a butterfly curve. So this is like the high to low transit, and then on the other side is a reset. Okay, and then you have the two resistance. This is in log scale, so that's why you have some curvature. Okay, in the linear scale you will have straight line, but this is in the log scale, linear curve will become something like this. So here anyway, so if you combine the one selector with one R1, you have this one S1R. So then, so here you see that, let's say the selector and one R only is the dash line, which is this one. Okay, so then if you combine those two together in series, then if you measure the current versus voltage, you get this red curve for this one S1R. So here you see that this is your right voltage, V right, and then your V read will be somewhere here. You can still distinguish two current level, 1 and 0. But then here at small voltage, you see the current is exponentially lower, right? So what do we care about? For example, this depends on your right skin. We just talk about the, for example, V over 2 skin, right? If your right voltage is here, then here at V over 2, this is the current you will get, okay? So that means for those half selected cell, because they will see half voltage, right? So their current will be orders of magnitude lower than what you have here, okay? This help to minimize the sneak path current. So here we can define this nonlinearity ratio, N. Okay, this is important. You have homework or even exam questions on this. So by definition, we just talk about that. This depends on the red skin, right? So here, let's say for V over 2 right, we are going to define the current ratio. This is on the right-hand side, the zoom in of this green box region. Okay, on the right, this plot is just a zoom in of the green box. Okay, so here we are going to define the ratio as here the at red voltage, the current versus half red voltage on the low resistance state current, because here you don't know the half select cell is high or low, right? Could be high, then the current will be even lower, but you have to assume the worst case, right? The half select cell could be low resistance, therefore you have the current here versus current there. So those two currents, right? This two current ratio, right? So let's say if this is current V right versus the current half V right. This is current half V right, VW. So basically current V right over current V half right. That is the ratio. And this is for the low resistance states. Okay. So in this case, you see this is a little bit more than 10, maybe 20. This N in this case, about 20. Not that large, okay. In this example, if you read the scale, right, this is 1 micro, around 1 micro, this is 10, this is probably 20 micro. So it's about 20 in this case. Okay, any questions? Right, think about it. So along the same row for the V/2 scheme, right, we just discussed. This is your selected cell. If this, you have like 20 micron, right? For the right, at the right. Then the other cell, if they are in the latent state, they may contribute 1 micron each, right? Ideally, you want this as small as possible, okay? So here, if you do this very well, you can have something approaching the ideal selector instead of the exponential IV. So here, those kind of devices may provide you the threshold IV. We call threshold IV. That is like a abrupt turn on above this selector threshold voltage. So if you have this combined with this R1 device, then you have something like this. Okay, something like this, 1S1R. But this one actually is very, the design margin is very tight in this case. You will see that. So the reason is that here, for example, if your voltage, right voltage is like 2 volts, then your half right, will be 1 volt. So this 1 volt is very approaching this turn on voltage. If there's any variation, right? So what if it's here? Then actually it's turned on. So you do have a large current flow, right? If there's any variation of this turn on voltage. So for this example, you may prefer the V/3, right? So V/3, that means the unselected cell will only see the voltage 2, right? This is 0.6 or 0.7 volt, right? Let's say 0.6 or 0.7 volts. Somewhere here, then it's more safe, right? This is away from, this V/3 voltage is away from this turn on voltage, this threshold voltage. Okay.
The right, is it same for the low resistance rate and high resistance rate? It looks like both the curves are converging to a point.
So you mean on the other side?
Like to be right in the previous slide that was pointed out.
This is just an example. Those two devices are not the same. So the voltage here is 2 volts. The other one, I don't know which one.
Right. If you know, is the upper curve is high low resistance and lower curve is high resistance.
Okay, so after write is successful, you will always end up with high current, right? So you need to account at the transition. Let's say, of course, it's a dynamic process, right? You start with low current and then you jump to the high current. So in the real operation, you will end up with high current, right? At the end of the set or program phase. So always consider the worst case, which, high current, low resistance states. Okay. So here is just a comparison of those two types. One is like exponential IV on the left hand side. So we show you the combined, which is a blue curve in this case. And then the threshold IV on the right. So here I have some notes here. So the selector device characteristic must match the memory device characteristic because those voltages very sensitive, right? So the turn on voltage, write voltage, read voltage, you have to design those voltages well. But here the drawback is that you see that after you add the selector device, the write voltage will increase, okay? Increase the write voltage, VW, right? So here you see that previously your write voltage is here, now you move to here, right? This is because you have to turn on the part of the voltage will drop on the selector to turn on it first, and then the rest of the voltage will drop on your memory device. So you increase the write voltage. So here for the exponential IV, the read margin is degraded because here the on-state current also suppressed by this exponential curve. So the read margin here is not as high as here. Okay, this is the threshold IV. So here the threshold IV, the read voltage has to be boosted above the threshold voltage of the selector. Okay, so there is a problem of the threshold IV. There is a holdback voltage. So I will talk a little bit on that. So the threshold IV actually, this one is not a full story. Typically, the threshold IV will turn on it like this way, but when it turn off, it will follow this path. Okay. So this turn on voltage, and then this is called hold voltage. Okay. Hold voltage is kind of small. So that means once the selector is turned on, you only need a small voltage to hold the on state. In other words, so here first you need to turn on the selector. For example, here you apply 2 volts to turn on the device, including write the R1 cell. But once you apply 2-volt voltage across this 1S1R, once the selector is turned on, you only need, for example, 0.2 volts or 0.3 volts to hold the on state. That means the rest 1.8 volts will drop on the R1. Okay, 1.8 volt will drop on the R1. Drop on the R1, which is good for the write. This is good for the write because you get most of the voltage drop on the R1. But what if you do the read operation? Because read, you also need to turn on it, right? Below that, you cannot distinguish any states. So that means read voltage you have designed somewhere here. Let's say 1.2 volts. 1.2 volts, you turn on, okay? After turn on, you only need 2.2 volts for the selector to hold the voltage. That means there's 1 volt across the R1, even in the read condition, okay? Right, so here, if the VR is here, so here I say the VW is 2 volts, and the VR is 1.2 volts, then there's 1 volt drop on the R1 for read. This might cause disturb, right? You need to turn on this above 1 volt, but once you turn on, then most of the voltage drop on R1. That will potentially disturb the states. So this selector design, I mean, is very tricky. The design margin is very small. And also you need to consider the device vibrations, noise, and so on. So it's a very difficult design problem. But anyway, so in the research community, people have spent, even I spent quite a few years working on this selector problem. Identify the design margin, different physical mechanism to have this kind of either threshold IV or exponential IV. And one more thing I didn't mention too much, the rectifying IV, which is like a PN junction. Silicon diode will work, but this is unidirectional. So those two are bipolar, which will be useful for R1. But then you could have unipolar, one directional, IV, right? So we talk about the threshold and exponential IV, but here for the rectifying IV, it's just one directional. The other there's no, for the p-n junction, there's no other side, right? Other side is, always like small current. So this could be useful for phase change memory because phase change only one polarity, right? You set and reset with the same voltage polarity. So this could be used for the PCM, and I will show you some examples later in the PCM lecture. I believe the first generation chip, which was like 2012 from Samsung, 8 gigabits phase change memory chip, use a silicon diode as a selector. But then if you use silicon diode, it's a front end of line processing. You cannot do this 3D stacking because silicon, you have to make silicon from the substrate. There's no way to do single crystalline silicon on top layers. But anyway, we'll talk about that in more details later when we talk about the phase change memory. So under the threshold IV, there are different physical mechanisms. One is called this OTS, Ovonic threshold switch. This OTS actually is used for the later phase change memory products, for example, 3DX points from Micron and Intel. And this OTS recently become popular again, and we will talk about that in the phase change memory lecture. So recently, in just like last year or two, SK Hynix and Samsung revisit this OTS device, and then they propose a new concept called selector-only memory. So I will talk about that later in the phase change memory section, but this is important in terms of the technology developments. And then the other one is called this insulator metal transition, and there's some academic progress on that, but no industry adoption. So this one basically the material will change between the metal phase and the insulator phase, and the challenges there is on-off ratio is kind of small. So here in the exponential IV, there are different kind of mechanisms, and actually I think something wrong. So this one CB run should, this one should, okay. So something wrong. So this one belongs to the threshold IV. I'll talk about that. And then for the exponential IV, IBM spent quite a few years developing this mixed ionic electronic conduction, which actually the mechanism is kind of tricky. I never understood because they never published the details. But anyway, they provide the IV, it's like exponential IV. And also if you can use some tunneling mechanism to get the tunnel current, which is exponential. So we'll talk about some of those in the next few slides. For example, if you engineer the junction or the band gap and offset very well through this, for example, the multi-layer oxide. You can close the door. So the currents could be, exponentially modulated by the low voltage versus high voltage, right? Because here, if you look at the band diagram, right? So in the low voltage, then here you have different oxide. Let's say tantalum oxide, titanium oxide, which has high and lower band gap. And then at low voltage, then the tunneling current needs to go through the entire stack. So it's pretty small currents. At high voltage, the band is bending. And then you have only here one layer to tunnel through. So this is, kind of this FN tunneling stuff. So as a result, you have this kind of exponential IV of this two-terminal device, just a multi-layer oxide. And here you see that the exponential IV. So here you do get a few orders of magnitude lower, right? So here you have to define it. So here they define it as a real voltage, but this is the wrong definition, okay? The real definition should be, you should consider the right operation. And then here V right, and then here V over 2, and then you look at the ratio. Because the right is the worst condition compared to the read. Okay. So then this OTS mechanism is also very complicated. So it's never fully understood in the community. But this OTS is based on the chalcogenate material, which will be the same, or at least let's say similar to the phase change memory. It's like this germanium, antimony, tannerite, and kind of alloy. So this OTS will have this kind of threshold switching behavior. So here it shows the so-called snapback behavior. I will spend a few words on this snapback. So here you see that as you ramp up the voltage, at some point, then it will have this kind of snapback and then go to the on state. Okay, so the reason you see this S shape versus N shape, I need to spend a few more words on this IV plot. So what we showed you before is N shape, okay, in the threshold IV. The reason N shape, why is N like, is that N shape? But anyway, it's like this, okay. So the voltage is continuous, but the current has sharp transition, okay. The reason you got this kind of IV is because you sweep voltage and measure current. Oops. And measure current. So that's why your voltage is continuous. You sweep, you force the voltage to ramp up, and you measure the current. So your current will jump. So in this measurement, it's you use a current source to sweep the current and measure the voltage. Then you will see this S-shape stuff, right? Because current is continuous, you ramp up the current and measure what is the voltage here. Then the voltage will have this snapback. Essentially, that's the same. Actually, if you do that on the same plot, right? If you measure the current, then basically you collect this point and this point in this S shape versus this, I don't know how to call it, N shape, not like N, but anyway, this. So you got the difference? It's the same thing, just a different measurements scheme. So here in this OTS, the mechanism is not well understood, but at least people think this is due to some trap stuff in this chalcogenate material. When the trap is fully filled, then it can, with high voltage, it can create another conduction path. Therefore, you turn on the current. So this is like the phase change memory because it's similar to the material system. But the only difference is that here in this OTS, after you turn on, then it will not memorize the state, unlike phase change memory. So if you turn it on, once you go back to the 0 voltage, then the on state will be there. So in the OTS, after you go to the 0 voltage, the on state will disappear. You know the key difference between switch and memory. What's the difference? Let me ask. What is the difference between a switch and a memory? Switch, I mean, for logic, you don't remember, okay? You just turn on and off. After you go to the 0 voltage, you go back to off. Memory, right? After you turn on it, go to the 0 voltage, still on. That's the difference. So in this phase change, let's say in this chalcogenate material system, it's probably that after you turn it on, then you do not create this melting process, okay? Because in the phase change memory, after you turn it on, you pass large currents, then you melt, and then the atoms are, in random location. So then this one probably just the electronic behavior without atom movement. But actually I don't know. And this is still under active research. Okay, but people measure this behavior and use it already. So that's why here I said current not large enough to trigger the structural change. That means to move the atoms. Okay, only some electronic conduction happening there. So here this volatile switch. Another one is this insulated metal transition. So one particular material is NbO2 niobium oxide. So depending on the temperature, it will change the crystal structure, and then you will have this abrupt IV. So the problem of this, yeah, this is perfect, like, you know, turn on and off. But the challenge is that the on-off ratio is not that high. It's only like 10 to 100, less than 100. So it could work for some small scale array, but it's very difficult to support large array. And also people proposed with some like CB-RAM, we will talk about that later in the R1 section. So it's conductive bridge random access memory. So for example, if you have some filament, let's say you apply some voltage, and then you will drive in the metal, for example, here the silver, into the oxide. So you will build some metallic conductive bridge. But what if the bridge is, let's say, not stable? So in the memory, you want the conduction bridge to be stable. So you can remember the state after you collect those two electrodes, you pass the current, you want the bridge to be stable. But here you want a weak filament. So after you remove the voltage, this filament will dissolve by itself. Then you go back to the off state here. So as I mentioned earlier, so the difference between the memory and switch, here you want a bad memory, poor retention. With poor retention, then you can use it as a switch. But again, this kind of device, I mean, there are some publications in the community. It never worked in production because the variation and the reliability not very well. Okay. From the nominal behavior, yeah, it looks good. I mean, on-off ratio pretty large. Let's say the N, the nonlinearity ratio, pretty large. Right? But then the reliability may not be good. Nevertheless, here we summarize some of those findings in the literature. Actually, I haven't updated this table. This was done quite a few years back. But even at that point, like 80 years ago, people have proposed different kinds of material stack for this two-terminal device with exponential IV or threshold IV. And then here I just list some of them. And then here the voltage range, you have to choose that the voltage to match your particular R1 or phase change memory characteristic. So what is critical here is the drive current density. So that is the on current density. You need to be high enough to provide the programming current. And typically you need that more than like 1 mega-amp per centimeter square. And the on-off ratio, then let's say the nonlinearity ratio N. So here you need like 1,000, right? If you, let's say for the back of envelope calculation, for the crossbar array, 1,000 by 1,000, let's say 1024 by 1024. The guideline is that your nonlinearity ratio should be larger than 1,000, right? Because you think about it, you pick one column, right? And then you want to distinguish the current on and off, right? But what if, let's say, other unselected rows, each of them contribute a little bit of current, right? If the on-off ratio, not on-off ratio, let's say N, the nonlinearity ratio, 1,000. If your 1,000 rows, other, let's say 1024, the other 1023 rows, each of that give you a little bit of current, 1,000 of that, right? If the ratio is 1,000, that will provide the same amount of current as your selected cell. Even from those unselected cells, 1,000 accumulation from 1,000, right? that give you the same current as your selected cell, then you cannot distinguish your selected cell on or off, right? So because from those unsafe cells give you such high current. So this nonlinearity ratio n depends on the array size. Okay. To enable larger array, subarray size, you will have larger n value. And also the device needs to have non-endurance, right? So every time when you read, you have to turn it on. So you have to have non-endurance. So questions? We will talk about the interconnect wire resistance, okay? So here it will become a problem if the wire width is scaled down below like 20 nanometer. If the wire is wide, not big problem, it's metal, right? Conductor current, the resistance could be small. But here, when you scale because those wires will be copper wires, right? Interconnect copper. But when you scale the copper in those sub 20 nanometer dimensions, the resistivity of the copper will increase. The reason is that the resistance of the metal wire comes from the mechanisms such as surface scattering, because electrons will, bounce back once it hits the surface of the material. If the surface to volume ratio increase, but because here below 20 nanometer, it's more surface than the volume, right? Electrons will hit more surface than traveling in the middle. Then your resistivity goes up. And also here the green boundary, right? With smaller wires, you see more green boundaries. So then the resistance will go up. So here, this is the calculated resistance per junction. Per junction means per segment from cell to cell per junction. The resistance will exponentially increase below 20 nanometer wire pitch. So here, this is ohm. So here at 20 nanometer, it's probably like 10 ohm. But if it's like 10 nanometer, it will be hundreds ohm, okay, per segment. That is very large. Why is that? Because here, the R1, for example, typically, let's say 5 kilo ohm. 5 kilo ohm, let's say your R1 resistance, unstated resistance, unstated 5 kilo ohm, right? If each segment give you, let's say, 100 ohm at this point, at 10 nanometer, with F at 10 nanometer, you see that 50 cells will give you the same 5 kilo ohm compared to the R1. That means, right, if you apply voltage to write the R1, let's say R1 is 2 volts to write, but you have to provide 4 volts to your R1, because half of the voltage will drop on the resistance here. But that is for the farthest cell, right? If you think about the problem, you have many wires. So you apply 4 volts here, and actually only 2 volts drop on the farthest cell. You can write this cell. But what will happen for this nearest cell across to the edge driver? This cell V over 2 will not work because your voltage is 4 volts. V over 2 means here you have 2 volts here. So this cell will also have 2 volts. You don't want to write it, but this 2 volts will kill it, disturb it. So this IR drop problem will make this margin, design margin, almost 0 if you have large cell interconnect resistance. But anyway, so here we have to evaluate the right margin, which is what we just discussed. Think about the worst case analysis. Okay, worst case. Okay, the last cell, right? The access voltage means actual voltage across the last cell compared to what you applied here. Okay. Or we write, let's say we write. And then for the read operation, what you care about is the delta I, let's say for the current mode sensing. So you care about from this column, what is I on versus I off, all those current will be, distorted due to this RJ junction resistance. So it's kind of complicated. So that's why a SPICE kind of simulation, netlist simulation is needed to evaluate this rate margin. So, but if you do that, then you can get this kind of plot depending on the nonlinearity ratio n, right? And also the array size, a nonlinearity ratio n, and here I've shown n by n, the array size. So here this access rate voltage, right? For 1000 by 1000 array, if your nonlinearity ratio is high, like 1000, you can still get like more than 80% of the rate voltage delivered to the last cell. But if your nonlinearity ratio is low, you see that you almost got nothing to your last cell. It's all like 0 voltage. You cannot write it, right? You can run the SPICE simulation. This is generated by the SPICE simulation by playing with those resistance values and then the nonlinearity ratio. So nonlinearity ratio basically will increase. Let's say if this is a cell resistance R, nonlinearity ratio will make n times this R here for those cells. So you can, construct a netlist and then do the SPICE simulation. So all challenges, I think I already talked about that. And then the nonlinearity ratio will matter, and also the wire resistance matter. So it's very difficult to scale below 20 nanometer wire width. So below that, unless you have some breakthrough in the interconnect material or use like SRAM, we talk about that, 3 wire lamps in parallel to drive the memory cell, then it's difficult to minimize the cell wire resistance. Okay, so last 10 minutes, we will talk about the 3D XPoint memory, which is a product from Intel and Micron. And this is one of the examples that the emerging memory really enters to the market. But of course, market tells the truth that the market doesn't welcome this new technology. So it becomes a failure in the business. But it's not a failure of the technology. I mean, the technology is good actually. So I will show you, okay, what the industry has gone through. So back in 2015, almost 10 years ago, Intel and Micron jointly announced they're going to commercialize this 3D XPoint memory. It's based on the two-layer design. So it's based on 1S1R, 1S1R. And it has two layers. So here in the middle, you have a shared bit line, and then you have another 1S1R here. Okay, and then you have 2 layers of VLAN, like this cross points stacked. Okay. So then when the technology was announced, then Intel and Micron didn't disclose too much details. So then here we have a lot of question mark. And again, this company I showed you many times, and the TechInsight, what does reverse engineering, right? So TechInsight bought one of those, chips from Intel and Micron, and then did the reverse engineering, right? Peel off the package and then, put it under the microscope and did even the elementary elements analysis, what kind of material, right? So there's rumor, right? This is phase change material. Is that true? And then what is the selector material? And then what is technology node? What is wire width, right? We talk about wire width matters, right? So a lot of questions, right? So here then I'll show you some reports from the TechInsight. So here is a 16 gigabyte single die in a package, okay. And then here the efficiency, array efficiency is pretty high actually. You see most of the area occupied by the memory. I prefer circuits a little bit. It's pretty well designed. And the density, if you normalize, is like 0.6 gigabit per millimeter square. Okay, this is a very high number actually. Even like 10 years ago, this number 10 years ago is higher than today's best DRAM, which is about 0.4 gigabit millimeter square. Okay, so this is a pretty good memory density. And here are more details. Okay, so Intel packaged it as the Optane memory as a product. So the technology is called XPoint, but when Intel sells the product, then it's called Optane SSD. They position this as a high-end SSD or storage class memory between, you know, the SSD and then the main memory. So here then the total die size of about 200 millimeter square, and then it has 5 metal layers. And then here what we care about is this one. Okay, the pitch is about 40 nanometer. That means the half pitch, which is F, is 20 nanometer. That is the wire width we just talked about. The word line, bit line, wire width, 20 nanometer. Okay, pretty small. And it enters that region where, you know, if it further scales, then the resistance will, you know, exponentially increase. It's just at that boundary. So, okay, so then those are overall like stuff. And then if we go deep into the technology, so it is verified. This is a GST-based phase change memory. And then the OTS selector is in series of this phase change memory. And OTS has 4 kind of elements. Okay, it's complicated. Okay. And then those 2 layers are stacked here. Okay. Above metal 4. Below that are some like peripheral circuits stuff. Okay. So here is those 2-layer memory. It's kind of small. There's a zoom in for that. And then this is cross-sectional view, and this is top view for the entire die. But I think they have the zoom in here. If you zoom in to this part, okay, you will see that the 2-layer, okay, 1S1R, for example, here, this middle is a shared bit line, and then on the top you have phase change memory and the selector here. Okay, again, this phase change memory selector here. So it's like this, and then selector, and then yeah, like this way. Selector, yeah, something like this. Okay, so here compared at that time, okay, if you compare, this was almost 10 years ago, right? So here the density, as I said, is like 0.6 gigabit per millimeter square. So compared to the DRAM at that time, which is only about, you know, 0.15 gigabit per millimeter square. So it's like 6 times higher density than the DRAM at that time. Even today, it's like 50% higher. Yeah. So, but this is less than the 3D NAND. 3D NAND at that time just started, right? But compared to the first few generations of 3D NAND, then 3D NAND at that time is about, you know, 2 or 3 giga. At that time, 2 or 3 gigabit per millimeter square. So this one is still like less than 1 giga. So it's like 3 or 4 times lower density than the 3D DRAM. So it's somewhere in the middle. Somewhere in the middle in terms of the density. So again, this is Intel's publication of this 128 gigabit 3D XPoint chip, I believe from one of the ISCC or IEDM conference. So here are more details include the timing. You see the write latency is like hundreds of nanoseconds, right? So it's a little bit slower than the DRAM, because DRAM is tens of, let's say 56, 60 nanoseconds in the read. And it's faster than the NAND, right? NAND flash is, you know, read a few microsecond to tens of microsecond. Write is even slower because of the, you know, the verify. So it will be like hundreds of microseconds. So this is faster, right, than the NAND. So again, from the density, both density and the latency point of view, this is somewhere in the middle, right? Somewhere in the middle. So that's why Intel position this Optane memory as some high-end SSD, and it sells in this module. You have two form factor, 16 gigabytes or 32 gigabytes. Okay, so you can plug in into your system. It's like instead of SSD module, you plug in this module. Okay, which provide faster speed. And also Micron announced a similar product they call X100 SSD. Okay, so Intel and Micron joint developed the technology, but later they, when they package that into different product, they sell differently. Okay. So even like in 2020, Intel continues the development. So at 2020, Micron first dropped out after 5 years. They didn't sell too much, volume, too much units of this one. So Micron stopped 2020. But Intel at that time continue, even demonstrate 4-layer. Previously a 2-layer, right? So you see this image from Intel's second generation of 3D XPoint. So it shows 4 layers. So 1 layer here, 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 here. So I have 4 memories stacked vertically. Again, this is not bit cost scalable approach. This is simply stacking. This is not the 3D NAND, which we talk about. You have to use one lithography and then save the cost. This one cost is not that low. You have to do layer by layer fabrication. Okay. But even Intel, they announced they stopped this Optane product and entire group dismissed. Okay, in 2022. But of course, Intel, suffer a lot from recent 2 or 3 years. Even today, I mean, Intel is in big trouble. But Intel's strategy, right? Because I know they want to focus on the logic. They want to, become a foundry. So they stop all other, like side projects, especially memory, right? So they sold the SSD to SK Hynix and also stopped the Optane memory business here. One reason for the business, okay, is failure. It's not technology. Technology is actually pretty good. You see that. So the business-wise, okay, one competition, because they position this as high-end SSD, but then Samsung also announced a product called Z-NAND, okay, a few years ago. So it used a single level cell 3D NAND, okay, instead of the TLC, QLC. So if you just do single level 3D NAND, the speed could be pushed to like microsecond speed, not too far away from this SSD. From this S3D XPoint, but the cost, the NAND is so cheap. So then this kind of product face the competition from this SLC NAND. Okay, performance-wise, maybe a little bit better, but cost-wise will be much, worse than the NAND. So that's why I don't know the full story behind this, but as a result, today, no longer exists. This product no longer exists. But as I said earlier, so this may come back because like SK and Hynix, SK Hynix and Samsung, they started this selector-only memory. So that is similar to this one, but get rid of this is 1S1R, right? So let's say you have this one, let me show you this. So 1S1R, what SK and Samsung is doing is to get rid of the phase change memory. They just use this OTS as a memory. And I will talk about that later in the phase change memory section, how this works. Actually, it's pretty nice. From the mechanism point of view, this sector-only memory, they call SOM. It's pretty nice. So it will save some fabrication cost because you no longer deposit this material, and also potentially this one will be faster and more reliable because it's simplified in terms of the process condition. But anyway, So that's what we have today for the cross-point memory. So any questions? Okay, so we will stop here. Thank you.